Hello everyone, welcome back to your online lecture on Mechanics of Materials 2, and for this lecture we are going to discuss strain energy. So far we discussed the concept of stress and strains, we have beams, we have columns, and the third concept that we are going to cover is the strain energy, which is part of the chapter 11 of your book. Now for strain energy, first let's define what it is. So strain energy is the energy stored in a member associated with deformation. So the energy is getting stored because of the work done on a sample. So let's imagine we have this member on the top right here. So member BC. Now we apply a force P on the area A, which is below right here. So we have a force P, and we have a certain deformation X, which is this one right here. Now the member deformed from BC to a certain BC with different length L. It's now L plus a certain amount of deformation, which is X. Now based on that deformation, we can actually write our force versus displacement curve. What do you mean by force displacement? So as we pull our this member BC right here, we have a certain displacement X. So if we're going to draw our force displacement curve, we're going to have something like this. And let's say it deforms to a certain amount, let's call it x1. Now, in order for us to calculate for the strain energy, we can take the area under this stress strain curve. So the area is now equal to our strain energy, and we can now call it as capital U. Now, how can we take the area under this curve? We take a slab, which is a certain P and dx. So this is dx right here, and this is a certain amount P. Let's call this one as P. And if we're going to calculate for the area of this curve or our strain energy, we're going to get U is equal to from 0, x1, so from 0 point up to this point right here, 0 to x1, P dx. So that's the equation for our strain energy. Now, before we move on to the next part of this discussion, this force versus displacement curve, it's also similar to what you discuss in your stress strain curve. And what do we mean by that? So if you're going to write our stress strain curve, let's imagine we have a similar shape. Not similar value, but similar shape. If we have a stress strain curve, you can divide it into two regions. So you have your elastic region, you have your plastic region. So the first region right here, that's elastic, and that's your plastic region. Now, which means your strain energy on the top, which is P force versus your displacement curve, it accounts both your elastic and plastic region. So what if we need a certain amount of energy just in our elastic region? So for linear elastic deformation, so let's say we apply force to our member and we stayed in the elastic region, meaning that once we deform our sample from this point, so as we apply force, we're increasing stress. However, after this, we stop right here, which means we are in the elastic region. So how can we calculate the strain energy if we maintained our force in the elastic region? So for linear elastic deformation, so let's say we have, again, going back to our force times displacement curve. Now, if we are in the elastic region, part of the curve right here, or the curve in the elastic region, it's just a straight line. And this straight line right here could be defined by, we can say that this is P is equal to Kx. So this is just an equation of a line, and that would be your slope. So P is equal to K times X. And let's say we want to determine the area of our curve. Obviously, it's just a triangle, but let's use our integral to get the equation for our strain energy. So we can define U is equal to from 0 to x sub 1. So let's say this is x sub 1 right here. So as P, or we can call it Kx because that's P. Again, we take a slab right here, P dx, so Kx dx right here. And again, this part, that's actually your P, is equal to 1/2 K, it's called x1, so let's call this one as x1 squared. Now, or we can also say that our U is equal to 1/2 P1 x1, and that's because, and that since K is equal to P over X, again, just going back to that equation there. So we have this equation if we have we maintained our force in the elastic region. So that's the description of strain energy. Now, the second term that we're going to discuss is the concept of strain energy density, which is small u. So now we have strain energy density, which is, let's call it small u. I'm going to put underline right here just to note that that's a small u. Now for strain energy density, that's the amount of energy per unit volume. Amount of energy per unit volume, which means if we have a strain energy, we just have to divide it by its volume. Now, this strain energy density, it eliminates the effect of your geometry. Just going to make this one bigger. So this one, it eliminates the effects of geometry. So how can we write the equation for strain energy density? So again, it's small u, one underline, is equal to big U, which is your strain energy, divided by your volume. Now, your volume can be described by area times your length. So A is area, and L is equal to length. So just imagine if you have a cylinder, that's the area times your length, and that would be your volume. So we can also rewrite this as U divided by V, just this one, is equal to the small u right here, is equal to, so from 0 to x1 p dx over a L, which means that this u right here, this is this u, including this 0 right here, and this volume right here, that's your AL. Now, we have that equation, and recall that we know that stress is equal to P over A. And we know that our strain is equal to amount of deformation divided by your original length. Again, going back to our example in the slide right here, so we have L becomes L plus X. Now our strain is defined by X divided by your original amount of L. Now that's force P times the area of your cross section right here. Now moving on, so we have the equation for stress, equation for strain. So now we can simplify our equation. So now that's your strain energy density small u, capital U divided by V, and that's equal to, again, 0 to a certain amount of strain, E sub 1. So this P divided by A, we can now simplify it into sigma x, let's say, applied along the x-axis. And now we have XL right here, or Vx over L. Then we can now have here the strain in the x-axis. So your E sub 1 is your elongation. Now that would be the equation for our strain energy density. So now again, just to have a quick recap. So first we have strain energy equation, and then another is we have strain energy density equation. It's just dividing it by the volume of your section. Now, what would be the units of your strain energy density? So for the units, we have for small u units, so we have small u is joules per meter cube, so energy per amount of your volume, or we can also have pound inch per inch cube right here. Now,